SysML V2 Lesson 10 Interfaces as Definitions. Welcome back to the SysML V2 Deep Dive series. In the previous lesson, we looked at conjugation. We defined a charging port once, then used tilde charging port to mathematically reverse its directed features for the vehicle side. In this lesson, we move from the endpoints to the connection itself. So far, we have a charger port and a vehicle port, but the thing between them still matters. A charging cable is not just a decorative line on a diagram. It can have resistance, length, rating, latency, shielding, material properties, and safety constraints. That is where interface def comes in. In SysML v1, if you wanted a connection to have its own physical properties or internal structure, you had to type the connector with a specialized construct known as an association block. SysML v2 makes the connection's physical nature much more native to the language. According to the SysML v2 specification, an interface def is a connection definition specifically restricted to connecting ports. Furthermore, every connection definition is mathematically a specialized part def. This means it declares the endpoints of the relationship, but because it is structurally a part, it can natively hold its own values, physical properties, and internal components over its lifetime. For our charging example, the endpoints are already known. The charger has a normal charging port, and the vehicle has the conjugated tilde charging port. Now we need a blueprint for the cable or protocol that connects them. The basic pattern is, first, define the compatible port ends. Then, define an interface def that names those ends. Finally, add any attribute or structure that belongs to the connection itself. This is the key shift. The connection is not only a relationship between things. Because an interface def is mathematically a specialized part def under the hood, the connection itself is a structural part with its own definition. That lets us talk about the connection as something engineered, not just something drawn. Here is a charging interface definition that continues the previous lesson's example. Let's walk through it. First, we create the package, interface definitions, and import two things. The ISQ import gives us access to standard quantity concepts. The charging system import brings in the port definitions from the previous lesson, including charging ports. Now we define the interface. This is the blueprint for the connection. It is not yet actual cable connecting one specific charger to one specific vehicle. It is the reusable definition of what a valid charging cable relationship looks like. Inside the interface, we define the ends. This says the interface has two port ends. The charger side must be typed by charging port. The vehicle side must be typed by tilde charging port. That matters because it preserves the compatibility rule from lesson 9. The cable is not allowed to connect two charger side ports. It expects one normal port and one conjugated port. Then we add a property of the connection itself. This attribute belongs to the cable relationship, not to the charger and not to the vehicle. This is why interface def is powerful. We can model the fact that the cable has physical characteristics. A longer cable may have different resistance. A different connector assembly may have different current limits. A future version of the model might add length, maximum rated current, insulation class, thermal behavior, communication latency, or certification data. The connection now has a blueprint. Because the interface definition declares its ends, the model becomes easier to check. If we use charging cable, the tool can see that one end is supposed to be a charging port and the other end is supposed to be a tilde charging port. That means the tool can reject or warn about invalid pairings, such as trying to use this interface between two vehicle sockets or two charger plugs. The interface also gives the connection a place to hold engineering data. Instead of hiding cable resistance in a comment or spreadsheet, the model can carry it as an attribute of the relationship. So the line on the diagram is no longer just a line. It has typed ends, semantics, and properties that other parts of the model can refer to. Before we wrap up, keep the distinctions clean. Port def defines an endpoint. Tilde uses the conjugated form of an endpoint, reversing directed features. And interface def defines the connection relationship between the compatible port ends. This is the natural progression of the last few lessons. First, we defined ports, then we learned how to conjugate them, and now we are defining the relationship that connects them. Here is a quick side-by-side recap. In V1, a connection was often treated mainly as a diagram line, unless the modeler added extra structure via an association block. In V2, when the connection matters, we can define that structure directly with interface def. Instead of relying only on visual conventions, the V2 interface definition can say exactly what kind of port belongs at each end. And if the cable has resistance, latency, or another property that belongs to the connection, V2 gives us a natural place to model it. That is the main value of interface definitions. It turns the connection into a first-class structural part of the model. The cable, protocol, or medium between two ports can have a reusable definition, typed ends, and its own engineering properties. In the last few lessons, we defined the blueprint for the connection. In the next lesson, we finally use it. We will look at explicit connections with connect, where the parts, ports, and interface definition come together to create the actual system topology. See you there.